Hi, today we're going to be taking a look at what we call slope fields. Now, slope fields give us an idea of what a function looks like. However, because the antiderivative is not unique, there can exist many functions. We've talked about that before. That's that constant. That's that. Remember, we take an antiderivative. That's that plus c that we have that gives us all the same derivative. As a result, a slope field will generate what we call a family of solutions, all of them looking exactly the same. We're going to talk about how to solve for the particular solution for later on in this section too. So first thing we do is how to draw a slope field. So they give us a derivative. Remember, this is a derivative. All the derivative does is it says it finds the slope. And I got this graph right here. So what I'm going to do to draw a slope field, very simple, is I'm going to plug in points. For example, I might go from -3, 2. At the point -3, 2, if I want to find the slope of that function, I'm going to plug in my x value. So it says -3 minus 1. So -3 minus 1 is -4. So what that's telling me is at this point over here, -3, 2, I have a slope of -4. So I draw a slope of -4. And I keep going, but you're going to notice right here, all the x values have the same. So all of these x values are going to have the same slope of -4. If I go to the next one over here, -2, 2, its slope, plugging it in, it says -2 minus 1 is -3. And likewise, all of these will have the slope of -3. Now, I'm guessing about what the slope looks like at -3. It's not perfect, okay? The next one, -1, 2, to get its slope, -1 minus 1, and I get -2. So everything here have a slope of -2. Whoops. Not perfect again, but you get the idea. And do the next one, 0, 2. I get m equals 0 minus 1, or -1. So everything at 0 is going to have a slope of -1. If you notice, it looks like it's starting to kind of turn as we kind of go. The next one, let's say 1, 1. The slope here will be 0 because 1 minus 1. So all of these will have a slope of 0. And if I go 2, 1, the slope here will be 2 minus 1, which is just 1. So now we're going back up. And if you kind of notice, we're getting kind of a shape here. Let's try the next one. 3, 1. Its slope will be 3 minus 1, which is 2. So all of these will have a slope of 2. And I can kind of guess what shape it is. What shape does it look like? It looks like it's going to be kind of like a parabola here, right? So it looks kind of like a parabola. Now, but if you notice, there are infinitely many parabolas here. There's lots of them. And if you notice, they all have a vertex at x equals -1. So I can say the vertex is at x equals, +1, not -1. Now, how can I confirm that this is a parabola? I can solve the differential. dy dx equals x minus 1. Like we did before, x minus 1 dx. Isolate your separate your variables, and then take the antiderivative. We get y equals 1/2 x squared minus x plus our constant. And we start to see more of a relationship with the constant. Remember, this constant says the constant says that there are many functions that have the same derivative, and we can kind of see that. In other words, it's an indefinite integral. So depending on what the c is, determines where it is on my function is going to be placed on the graph. Alright, now the next one's a little bit harder because I have both x and y. So what I would do is I would list out all the points. -3, 2, -3, 1, -3, 0, -3, -1, -3, -2. And I would find each of their slopes. For the first one, I get a slope of -5. Here, -3 minus 1, my slope is -4. Here, -3 minus 0, -3. Here, my slope is -2. My slope here, -1. You can verify that because 3 minus a -2 is -1. So when I go here, my slope starts off at -5, very steep, -4, and it keeps going, like so. Now, I'm not going to do all of this one with you, but I'll show you what it looks like in the end over here, okay? In the end, this is what our graph looks like, right here, plugging in all the points. and we plug in we get all the slopes, and so on and so forth. I kind of went backwards here, but you get the idea. Now, what I want to pay attention to here is, notice here they all have a slope of 1. Well, that's probably telling us that that's a slant asymptote right here. So the next thing they tell me to do is plot a point at negative 2, 1, which is kind of what I did right here. At negative 2, 1, I plot a point. And I'm going to graph this function. This is called a particular solution. So if I were to graph it, ready? If I head towards the left, notice the slope field is directional. It's telling me to go. The slope here is negative, so if I go to the left, I have to kind of go up. If I head towards the right, somewhere around here, notice 0 slopes here. Around here, my slope is 0. So it goes to 0, and then it goes up. Follows the asymptote forever and ever and ever. Okay? So try this one. It's kind of a fun one right there. Okay? And then let's take a look at the next one on the next page. Alright, now the last one, pretty easy to do. Now, notice for this one, I don't have to write all the points because I'm only interested in the y's. So I look at the y's here. My y's are 2. So if y is 2, I know my slope is going to be 1. So everywhere the slope is 2, I can write a slope of 1, 1, 1, 1, 1, 1, 1. When my y value is 1, my slope becomes 1/2. I'm not interested in the x's here because it's not a part of my derivative. So 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. When it's 0, my slope is 0, 0, 0, 0, 0, 0, 0, 0. My slope is negative 1. My slope is negative 1/2. Negative 1/2, negative 1/2, negative 1/2. And I keep going. And when my slope is negative 2, we get m equals negative 1. So negative 1, negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. Now this is kind of a weird looking graph right here, but again, what I want you to notice is this part right here. It kind of looks like that there is, again, an asymptote. And I can use that. So let's say I wanted to, remember, this is a family of functions, a whole bunch of functions right here. Okay, but let's say I want to find the particular one that goes to the point 0, 2. It says 0, 3, 0, 2. Here's 0 up 2. And I want to graph this particular function. Well, what happens is, if I go towards the right, it goes down. It's going to follow my slope field. It's going to approach the asymptote and never reach it. On the other side, take a look. It's positive. It's going up. So it's going to go up. So there we go. And if you notice, this kind of looks like our exponential function. And we can verify that by solving. That's what they ask us to do here. What is the parent function? To do that, we have to solve the differential. So I get dy dx equals 1/2, right? Isolate y, separate your variables, 1 over y, dy equals 1/2 dx, right? Then we integrate both sides. We get the natural log of the absolute value of y equals 1/2 x plus c1. Exponentiate both sides with the absolute value of y equals e to the 1/2 x times e to the c1. Remember, we can rewrite that like that. And now we're going to let e to the c1 equal c2. Remember, you have to show all of these steps, right? So we get the absolute value of y equals c2 e to the 1/2 x. And what does that give us? And when I solve it, I get y equals plus or minus c2 e to the 1/2 x. Now remember, we get two answers here, the plus or minus, but look at the graph. We can kind of see that. The positive one is above the x-axis. The negative one would be the same one, but reflected. That's what negative means. It's a reflection. It would go below. And that's why it's important that we have that plus or minus. We can see that plus or minus in our slope field. Now, but for this one, we want to get the particular solution. So to do that, we use our initial condition. So we now need to find C2 by plugging in the point 0, 2. And if we plug it in, we're going to look, remember here, y is positive. So if I plug it in, we get 2 equals C2 e to the 0. So C2 is 2. So my function there is y equals 2 e to the 1/2 x. And there's our function right there. So we kind of hit on a lot of different topics here again that we haven't seen in a while. So take a look at these. They're not that hard to do. Okay, and I'll see you guys in class. Bye.